let's refresh on how we propose mechanisms, the rules involved, and what we need to think about as we draw mechanisms. So keep in mind that there are really sort of limited types of mechanisms. Three main types here. The first one involves strong electrophiles. So that will be maybe acid catalyzed reactions or something where there's a plus charge. So in HCl, maybe the H plus is involved. If we have a secondary carbon, we could have a bromide leave, and then we'd have either a full carbocation or at the very least a partially positive carbon because of that carbon-bromine bond, and so a good electrophile. Something like BF3, we have an empty p orbital, and so it's accepting of electrons, and so an electrophile. Another type will involve strong nucleophiles, so we recognize these by their electrons. So hydroxide or an amine with its lone pair. The Grignard reagent, where we talked about this being a strongly negative carbon to this plus charge on the ions. A third type will be radical reactions, and those kind of have a very special category that we saw back in chapter 4, and we don't encounter that as often now. So in order to figure out what mechanism we have, how to predict a product, we should look at the conditions and catalysts involved to determine what type of reaction we have. So here's an example reaction, an alcohol and a T-butyl bromide with acid present, and we end up getting this T-butyl ether with H plus and Br minus left over. So it's this acid present that tells us it's an electrophilic kind of reaction. So we can probably imagine that this T-butyl bromide could actually form a carbocation because it's in ionizing conditions because of that acid, and so this bromine carbon bond can break, forming the carbocation. And now our alcohol, our OH, with its electrons is able to act as the nucleophile to add to that C+, and that will give us an intermediate that is charged. And it still has its proton present. And so then the next step could be that proton comes off. We often use some sort of base to do that. And so in the case of this kind of reaction, we could use bromide to act as the base and remove a proton, and that would end up giving us our product here. So look at all the conditions involved so that you can figure out what should happen in this previous page. We saw that we could do one arrow in each step. So the way that you do this, draw all the bonds and substituents of each carbon atom. You probably saw in the last that I tried to limit my line angle drawings to other parts of the molecule, and we'll focus in on a carbon where a reaction might occur and draw all the bonds in for that. Only do one step at a time. So in this particular example, I've got a carbon with a bromine, and it's a leaving group, and I've got a good nucleophile, and so I can imagine that attack, but I'm not going to draw everything at once. I'll use my curved arrows to show one step at a time. So in this case, we have a concerted, right? We have to attack, and then the next thing happens. So it depends on the type of reaction. This can be 2 steps because it is concerted, or 2 arrows in 1 step because it is concerted. And we always draw from the nucleophile, so that's where the electrons are, right, to the electrophile, where the electrons are not. So our 5 basic rules here. That is fundamental, not base, because we're going to talk about base in a minute. Never create a primary carbocation. In this case, I gave the example of a methyl, which is even worse than primary. So this is no, but this is tertiary, and so this is fine. Secondaries are okay, but we don't want to create primary or methyl carbocations. Never create an acid in a base. So if you're doing a reaction and all of a sudden you make a proton fly off and the whole reaction was in base, that would not be good. So don't create a proton in a basic environment. And then the parallel to that, of course, is don't create a base in an acid environment. So that's why at the beginning we talked about pay attention to what are the conditions. We also say never create a dication or a dianion. Now you'll find in some rare examples that we do this, but as a general rule, not. And then, of course, pay attention to the number of bonds to your atoms. Never do you put more than 4 bonds to carbon. So if you end up with something like that, you'll get this little message that says TMBC, too many bonds to carbon, because, of course, that will not work. And then other atoms as well. So remember that halogens just get 1 bond. There are going to be some rare occasions where we show 2, but then of course the halogen will be charged with a plus. So we'll get to that. And pay attention to the rest of your atoms. So if you have an oxygen, you can only have 1, 2, or 3 bonds to it. And if you have 3, there needs to be a positive charge. If you have 2, no charge. If you have 1, a minus charge. So pay attention. Remember, what you see is what you get. So don't use reagents other than those that are shown for you, that are provided. Sometimes you might have to make a guess because you're trying to figure something out, but that's you have to then use some context. Use curved arrows to show electron movement. Remember, we use a curved arrow that moves electrons from where they are to where they're going, the positive. Proceed logically and stepwise, so 1 step at a time. So here's a reaction. You may remember, well, this is just an atom, but you remember an enol. And you remember that enols would tautomerize to the keto form, and they could do so in acid or base. And so you might draw your keto form, and then you wonder, how should I get there? Well, if you're not given anything, go back to before you formed the keto enol and say, what conditions was the molecule in? What conditions formed this? And you might find that you were in base, let's say, for example. And so that means that I'm still in base. And so then my first step would be to remove a proton. And that will create an anion, right? I have an anion here. I can create an anion. And then I'll move the electrons down. So let's create that anion. And then when I push electrons down here, I have to push them somewhere else. So that has to be a concerted step. So then I'll form this anion. And then back here, when I took this proton, I formed water. So I have water present. And so that's where this anion can take the water, and we form the final product. So we moved atoms around, and what we did it in depended on the conditions before that enol was even formed. So here's how we can use the mechanisms. We can use them to help us predict the major product. So for example, on this one, we see we have an anion. The sodium would be a cation to this oxygen anion. So this is an ethoxide. And so that should act as a good nucleophile to this polarized bond and kick out the chlorine as a leaving group. And so then I'll say, oh, that's probably this product. And then you can keep track of the counterions. Dicyamylborane, well, you may remember that boron to hydrogen is a bond that will add across a triple bond, and the cyamyl groups take up space, and so that puts the boron out here. And then in the process of that, we're going to lose one of the triple bonds as it adds an H and a boron. And our cyclic part, there's an H that was already there. And then this part, it was quite a long, complicated mechanism that ended up replacing boron. And so I'll abbreviate here and say we end up replacing the boron, and so we'll have a enol. And then we recall that an enol formation results in the keto form as the final product. And then you say, oh, if I were to do the mechanism in that, would I do it in acid or base? Well, remember back here, we got our enol in base, and so then we could do a enol keto tautomerization in base. This final one, we can predict our product by saying a strong base and an alcohol. Well, those two could interact. I could take that proton. That will leave me with this anion. And then, oh, what if that attacks here and displaces a leaving group in an SN2 style reaction? That will give me 1, 2, 3, 4, 5, a 5-membered ring plus chloride. Plus water, because that was forming in the first step, and then that's where the sodium also ends up over here. And so we can use this mechanism knowledge to predict some products.